great pleasure that we welcome you all to the 17th inaugural lecture of the University of Mallikarachchi. With the honors of introducing our inaugural professor for the day, lecturer, Professor Chinthaka, Mallikarachchi, I wish to invite Emeritus Professor Prof.
Thank you very much for giving me this opportunity to introduce Chinthaka. I first met Chinthaka Mallikarachchi, or got to know him actually, when I was looking for someone to do some computer modeling on a small consulting project that I was involved in. So I couldn't find any among the younger members of staff because they were busy or otherwise occupied. And Chinthaka's supervisor, Dr. Ranasinghe, said that maybe you can take a chance on him. He was a final year student at that time. And Chinthaka proved to be very meticulous and committed to his task, and assisted me greatly in doing the computer modeling of this building, which had developed some defects, and we needed to find out why those defects were occurring. This relationship with computer modeling is something that has characterized our relationship over the years, including doing the model for the Lotus Tower, which Chinthaka did with great competence, because he had to develop the model for the Lotus Tower without getting it from the Chinese designers who were not willing to give it to us. But his model, we were able to compare the outputs, and they matched very closely with the Chinese outputs. And more recently, he was involved in designing involved in retrofitting of a water tank, where once again he had to model the expected behavior. So later that year, in 2005, the Joint Board of Moderators were visiting our department, and Chinthaka, once again as a final year student, had great maturity to sort of make a kind of liaison between the team and the academic staff members. He communicated to us some of their concerns that the Joint Board of Moderators had, and it helped us in our response. So soon after he graduated, of course, I invited him to be a research assistant on a SRC grant, which some of you know about. And I was only learning about about tsunami loads and resistance, but I don't know how well I guided him, but anyway, we were able to get a paper in the structural engineer journal. Now around this time, he was thinking of postgraduate studies. And a few students in the previous years had been successful in going to Cambridge. We had a long drought, and then about 2 or 3 years, there were people who had gone to Cambridge. So I wrote him a reference. I remember writing that although Chinthaka graduated 4th in his batch, that I would rate him first. That may have been a sort of, I don't know, personal opinion. And I don't know how well that helped him to get to Cambridge. But a few years later, when I met his supervisor, he told me that one of Chinthaka's references did in fact say that, although he was 4th in the batch on graduation, that he was rated first. So I am very happy that he was able to go to Cambridge. When he was there, because his supervisor went to the California Institute of Technology, I think Chinthaka had to take a decision whether to remain at Cambridge and finish there or go to Caltech. As it is, he went to Caltech, and although he didn't transfer his registration, a lot of time he spent at Caltech. And I think this gave him the best of both worlds in terms of, UK as well as US experience. And I think this is something that he has brought to bear in his career. So around this time, I was head of department from 2007 to 2010, and it so happened that I was able to visit the UK during that time. I don't know how many of those times I met Chinthaka, but I actively headhunted him to come back to the department. I remember once having tea with him at the Paddington station. I'm not sure that he remembers that. But fortunately, in 2012, Chinthaka did decide to join the staff at Morocco University. And I don't know, maybe you can say the rest is history, because in about 10 years now, he has become professor. I would like to read to you about his career from something I wrote as a reference for his Fulbright fellowship. I have said throughout his career, he has chosen to remain in technologically advanced research fields, something that very few Sri Lankan engineering academics have done. he has in parallel been able to attract the best and brightest of successive student cohorts to work on his projects, both at undergraduate and postgraduate levels. This has resulted in no less than 7 of his students going on to Cambridge University for their own PhD studies, 3 to Caltech, and 1 to the University of California at Berkeley, and many other places as well. This is just to mention what I consider to be top places. A truly noteworthy achievement in the span of 10 short years as an academic. Even more impressive is that 1 or 2, depending on the way you count, of the above have also returned to this department as faculty members after their own PhDs at Cambridge. So I would think that Chinthaka has fulfilled the promise that he showed as a student and a young academic. I am aware that he has got many research grants through the Senate Research Committee and also through the National Research Council, because I have sat on both of these bodies. He has got awards in plenty, including the Raghu Chandrakirti Gold Medal from the Society of Structural Engineers. And he has also, his collaboration has been sought by professors from Indian Institutes of Technology at Roorkee and Hyderabad as well. In the middle of all of this, I'm sure all who know him will agree that he remains a very unassuming person. In spite of his impressive research credentials, he pulls his weight in teaching in the department. I have left the department for about 2 years, but I'm sure that is the case, and also in administration. I would just like to sort of wish him well. I'm sure that we will be treated to an excellent lecture about the topic that he has chosen to speak to us about. I wish him well also in his Fulbright fellowship, which he has now obtained, I think. So, so let me invite Professor Chinthaka Mallikarachchi to deliver this inaugural address.
Thank you very much, sir. It's an honor to get introduced by yourself, and probably I'll refer to that towards the end of my presentation. Vice Chancellor, Deputy Vice Chancellor, Dean Faculty of Engineering, Dean Faculty of Graduate Studies, all of the deans, Head Department of Civil Engineering, all the heads of departments, my dear colleagues, students, family and friends who are here as well as joining online. It's indeed a pleasure to do this inaugural lecture. And I would like to thank Professor Ajit Alvis giving me an opportunity to forcing my teachers to listen to me as well as my family as well. So let me get this shared. Right, okay. From being a little child, I was always looking up to my father and wanted to become an engineer. I didn't know what are the subjects I have to take and whether you have to take maths, chemistry and physics for the A-levels, but just to become an engineer simply because my father who was an engineer. So that inspiration from my childhood led me today to the journey beyond gravity. So just by looking at the title itself, you would probably have 2 questions. First, isn't beyond gravity is easy because it's one less equation to solve, so it should be easy. And then the second, what does the civil engineer doing in space? Because as far as most of us are aware, civil engineers has to ground somewhere so that the structures has to transfer the loads. So in a little bit, I'm going to explain you why this happened and what are the reasons and why I ended up here. So hopefully during this lecture, I'll be able to give you some answers as well as maybe inspire some students. So get back to answer the second question. Basically, my research is focused on aerospace structures as title depicted, and also I'm working on the civil engineering structures, large structures, mainly computer modeling and similar areas. So today I would like to focus on the space structures part of it. And in fact, Professor Dias introduced certain things that why I ended up here, but at the same time, this is the exact structure that led me to apply to Cambridge, because this is actually, I saw this on website and it's a retractable roof, so I thought it would be interesting as a civil engineer to look into. But of course, when I went there, my supervisor said there are these other avenues. That's how I ended up here. Right. I was privileged to have experience of, in a way, best of both worlds. Both these institutes are ranked top 10 in the world, wherever you look at, whatever the ranking you look at. Cambridge, of course, has over 800 years of academic excellence. And Caltech owns NASA JPL, the Jet Propulsion Laboratory, which sends the Mars rovers to Mars. And also, it had the wind tunnel in the California region. All the aeroplanes were built in, manufactured in west coast of USA, were tested in this particular lab. So because of that, both these basically sort of helped me as well as nurtured me into this area. So getting back to the topic, hopefully at this end of the presentation, I would hope that you would understand what the space structure is, and I'm going to talk about what are the design challenges, change in environment, transport, and energy demand in space structures. And I will try to use a case study where I will sort of walk you through how design process would be and how you would approach it. And finally, I will end up with a couple of future applications and acknowledgements. So these are some of the iconic space structures, I would say. So people who were born in my time or before probably remembers this Mir space station. So it used to be the only space station available, and it's mainly a Russian one. And recently it was replaced by the International Space Station, jointly launched by several countries together. And then when it comes to telescope, Hubble telescopes used to be the one which dominated the world. And last year, the James Webb telescope replaced that. And now they are looking into even further as well galaxies, as well as with the planets and whether there are any habitats. And this Icarus solar sail by the Japanese Aerospace Agency, which I will come back to that, is sort of a step in future where they went into a larger solar sail. What is a solar sail? I'll get back to that in a couple of slides. And the Starship project by the NASA is another example that I'll discuss. And I'm sure all of you are familiar with these Mars rovers. So the NASA, especially the Jet Propulsion Laboratory, is exploring the Mars surface as well as subsurface conditions. So let me take an example, a solar sailing, as an example to explain these what are the space structures I'm talking about today. Solar sailing is analogous to wind sailing. Basically, photons emitted by the sun is hitting a sail or a membrane and get reflected, and that provides a propulsion to propel the aircraft. So this requires large surface area because the amount of energy you are gaining is very less. So you need a significantly large area. So because of that, the relative size is a bottleneck. Now, if I give you an idea about what we are talking about, this is an example of NASA solar sail. One of the solar sails is 160 meter by 160 meter. And that has to be packed into one of these spacecrafts. Right? But if you can't imagine, if you're not familiar with the Washington Monument, let me put in prospect to Sri Lankan conditions. So all of us know Colombo Lotus Tower. We are talking about half of the Lotus Tower. And in fact, it has to fit into not the launch vehicle, but the storage component of the launch vehicle is only a very small amount, because most of these things is for propulsion, and that will basically send off later on. So now somehow we have to pack this large configuration into a smaller compact stage. And this is an example where they are trying to explore, expand. So basically, essentially what we are saying is you need some sort of a deployable structure, which basically the research topic I'm presenting today, and that has to be light in mass and easily compactable for launching or basically sending out of space, so sending from Earth. So now, what are these structures and how you look at it? You always you look for nature and naturally inspired. So what you're seeing here is a blooming moonflower. I'll come back to that later on. This is recently used by NASA for one of the projects. So as you can see, when the flower is blossoming, it rotates and goes around and suddenly pops out. So these concepts are being in nature, and then you can make use of this. So as I said, so these structures need a large surface area or volume when they are in operation, but it has to be compacted to much smaller configuration during storage and transportation. So what are these structures, and which we call deployable structures? And the simplest day-to-day example that all of us are familiar is an umbrella. So you can keep the umbrella in your handbag or maybe in your pocket, and then when you're out with the sun or rain, you can easily expand. But if you think of the structural point of view, there are two extremes. One, it has to be soft so that it can bend and compacted. But at the same time, when it's in operation, it has to be stiff. For example, when you're holding an umbrella in rain, and if the rain droplets collapse the umbrella, then the operation is lost, right? There's no use. So because of that, these are two extreme cases in structural engineering you have to be looked into. And then the other problem here is if you think of an umbrella, you have to basically use your hand and push it out. So if you think in space structures, you have additional motors and also the energy source to deploy it. That means you have more mass, more weight, and more volume. So it's very difficult to send it out. So it becomes another bottleneck. Whereas if you look at the umbrella itself, nowadays there are umbrellas which you just press a button and it self-opens. So if you can make use of these, you can basically remove all these mechanical components as well as a requirement of energy in the long run. So these are called self-deployable structures. Simplest day-to-day example is a carpenter tape. So I'm sure all of us have used this carpenter tape. If you pull it out and then release, it will coil back. So in space, what we need is the operation in reverse. So these are some of the self-deployable structures that has been used. So if you look at this Boeing spring back reflector, you can actually see the Canadian flag through it. So it shows how lightweight is it. And also these are compacted into different configurations. So there are different examples. This was actually developed at University of Cambridge. So this small part, once you release, it comes back to this. It's the 1/16 scale of an actual structure that they intended. And similarly, there are other examples from European Space Agency and some other places. And then today, I'm going to focus more on what we call a deployable boom. So what you're seeing here is an example of an actual mission by the European Space Agency sent in 2006 and 7. The mission here is to look at whether there are subsurface water paths or water in mass. So in order to do that, they had these antennas. There are three poles. You see two dipoles, each having 20-meter long in length, and a monopole with 7-meter length. So you cannot fit into this 40-meter long boom in a spacecraft. So the idea is to somehow compact this and put it into a 1.7-meter cradle as shown here. So the concept they came up with, you slot this at certain intervals and you fold it here and then put it there. So once you go into space, once the clamps are released, this has to automatically deploy so that you don't need additional mechanisms and the power to deploy. This is another example where the German Aerospace Agency is using two omega-shaped cross sections together, glue them together. So you will have a circular omega-shaped section here, and then a flattened and coiled. So the idea is once you go into space, you release the clamp, it will deploy in a radial direction like this. And here you are seeing how they're going to, or how they're planning to deploy a 20-meter by 20-meter sail with 4 of these booms. So there will be 4 booms compacted at this point, and those will be going in radial direction while they are deploying. This will be dragging this sail. So that's how this deploys. And let me look at another example where this is the NASA JPL Starshade project. The idea here is to observe the planets around in the other galaxies. But the main problem is these are basically orbiting around sun or a star. So the light emitted from the star is so bright that you cannot see these. So the idea here is what we call the shade. So you shade the starlight coming from that, and so that the camera or the telescope can see the planets around. So let me show you a small video clip. So you have the original structure compacted here, and it separates from the spacecraft, and then the spacecraft rotates so that the telescope is pointing towards the star. And then once the structure or the star shade is fully deployed, it will go away at a certain distance from the telescope so that it will just cover the sun or the star so that you can see the planets moving around it. Right. Then if you think about again, now these are very large structures that we are talking about. And then how it will fit into a launch vehicle. Now, as you can see here, it's too big for the rocket. So all of us know about art of origami. So you can fold these things, do your trials with papers. This is actually a JPL. And then you can come up with a prototype, maybe a larger scale, and then finally you send into space. So if you look at this particular structure has two configurations or two structures in a way. Now what you're seeing here is some sort of a membrane type of a structure. If you can have a look here, I have a paper model where you basically, if you pull from two ends, this can deploy. At the same time, if you release, it will go back and hide now. So there's a membrane part of this structure. And then of course, like the umbrella, you have to have some sort of a structural configuration. So today, what I'm going to focus more on the structural configuration. So I'll take two examples and go through that, walk you through that. And so the DLR boom or the German Aerospace Agency carbon fiber reinforced polymer boom, as well as the MASIS or the MAS sort of three booms that the European Space Agency sent out. So let me take the MASIS booms first. So the concept here, as I mentioned before, you make slots and put it in a cradle, and once it goes into space, it has to deploy. So now if you look at this, it is folded here, and one by one it has to come out. And also this is a dynamic deployment, so it might go around, hit some part of the structure. So you have to, well in advance, you have to know what is going on. So remember now the original title said beyond gravity, and you would assume that it's the one less equation to solve, but the practical problem is this will be operation in space, but how you test them on Earth? Can you really do that? So now before I go into gravity, there are additional problems. Now what you are seeing here is the same boom. Now you need 40 meter long or at least 20 meter long space. So what they are doing is actually what they call the helicopter test. So you hang from a helicopter and deploy it and see how it behaves. Of course, the gravity is there, the air drag is there. And then this is a laboratory scale experiment. They have a very light friction, almost very low friction table, but still the friction, like when you deploy this, the friction of the table itself or the membrane itself will prevent it from deploying. And then the other issue is the air drag. So I'm not so sure how many of you seen that now. This is done in one of the NASA centers, Glenn Research Center. It's the largest microgravity system you have here. But now what I'm going to focus is on the air drag. Now, according to Newton's law, what we learn in A levels, we know like when you drop two objects at the same time, those two should reach, or those two should move at the same rate. Right? So now what you're seeing here is a heavy ball as well as some feathers. As you can clearly see, those did not travel in the same time, right? But the problem here is because of the air drag. Now, if you take this to a vacuum chamber, so now you don't have any air. Now you can see both of those fall at the same time. So clearly, Isaac Newton was right. So this is a slow motion video. Let me wait till it finishes. So as you can see, clearly air drag plays a significant role. It didn't matter in the case of heavy ball, but of course with the feathers it mattered. So we're talking about extremely lightweight structures. So if you want to do any experiments, that plays a major role. So we're talking about microgravity or zero gravity almost. So what are the facilities available? There are different techniques. Simplest would be the gravity offload system where you hang things from a cable. So the tensile force in the cable will sort of offload the weight of the structure. And then what I showed you is the NASA Glenn Research Center is the largest facility available on Earth. It can reach, it can keep you 5.18 seconds zero gravity. So we have very limited time. And the height is 140 meters and diameter is only 6.1. So if you remember the Mars's boom that I talked about is 20 meters in length. So it will not fit into 6.1 meter diameter. And then the other option is the reduced gravity parabolic flight. Both European Space Agency as well as NASA has that. So what happens is in this large aircraft flies in a parabola, and for a 30-second or 28-second period, you get zero gravity. And again, if you think about the size, it's 20 meters in length, 5 meters wide, and 2.3 meters height. So both examples I told you, especially the Mars's one, will not fit into this. But of course, we can do a component level or scale down structural testing. That's how we would design this. Now, let me go back to the other example where I talked to you about the deployment. German Aerospace Agency's this deployable boom. So the idea here is once you release the clamp, this should move in a straight line so that it will apply 4 radial forces to the solar sail so that it can deploy. So now, this particular structure will not deploy at all with gravity, and also friction and the air drag can prevent it too. So what you are seeing here is one of the tests that they did with parabolic flight. This is a long video, but I'll have cropped this. The first one, what you are seeing is without any control, the same structure put on a parabolic flight, European Space Agency's parabolic flight. So you can see it's coiled, and you are inside a large Airbus aeroplane. And one of them is going to hold this, and when the zero gravity is reached, they are going to release it. And the objective or the mission is to get a straight line deployment. So now the scientists are getting ready till they reach zero gravity, and once they do, you can see what we wanted is a straight line radial deployment, but clearly it's not happening. So, and if you think, actually what happens is not only this structure fails, but this can go and hit in the other part of the spacecraft. So that can destroy the entire spacecraft. So it's extremely important that you know these behaviors beforehand. Then they tried 2 different controlling mechanisms. So I'll not show the first one, but let me go to the final one, which is basically having an uncoiling mechanism from the far end, or in a way it's the carpenter tape in reverse. So you have coiled here, but in the carpenter tape, everything goes inside, whereas here it will be uncoiling from the end so that it deploys in the radial, in a straight line. So they are about to reach this 30-second zero gravity, and as you can see, it deploys in as a straight line. And you can see that person going and hitting his head, so it's clearly zero gravity. Right, so these are the challenges with experiments. Air drag, not having enough space or the large facilities, zero gravity, friction, and there are a lot of others. So because of these, virtual testing has become extremely important, and also the computational power develop very rapidly. It can be very useful. So most of the structures built before 2000 is being basically a trial and error process. But nowadays they are going to do a lot of computer simulations. But of course you have to verify them. So in order to verify, you need some sort of a experimental study. So let me take this opportunity to walk you through a single design case. So I'll take a case study and I'll show you different milestone and how we would reach this. So what I'm going to use is this what we call as carbon fiber reinforced polymer tube hinge. So it is, as you can see there, it's a hinge. It's the actual structure I have on my hand. So the idea here is you fold it like this, exactly what is shown in there. And then once you release the clamp, this has to deploy. Whereas in a normal one, you would have a mechanical system, a motor will rotate, and you need energy to put into this motor. and then only it deploys. The advantage here is when you are storing the energy elastically, you don't need that additional energy, just the stored energy itself will deploy the structure. Right. So this is what we are going to try to design and how you can actually fit into space, this concept, right? And also if you think about this, what I have here is two shells, curved shells. So it's actually this carpenter tape in, you're having two carpenter tapes. So that's the basic concept behind it. Right now, when you go into computer simulations, normal computer finite element modeling, you will have an elastic modulus and some material parameters to be 14. But in these structures, these are carbon fiber composites that we are using. So these have different nature of material, different behavior. So you need to study the material first, but we go for multi-scale modeling. So you look at the micrograph, look at these properties, and then come up with some sort of a homogenized or effective properties into the simulation. And once you can do the simulation, then you need a failure criterion to identify whether the structure has failed or not. So you have to come up with the failure criterion. And once everything is ready, if you can get all these properties correct, and if you are able to simulate, then we can think of design improvements or design optimization. So what I'm going to show you is this cycle, and finally I'll try to show you an example where a 2-hinge boom is wrapped around a spacecraft and whether we can design. So let me first focus on the micromechanical modeling part of it. So as I said, this has a very complex structure, but for the computer model, if you look at this hinge model, what we need is just some effective properties, what we call the homogenization process. So on the left-hand side, you have the detailed material, and then you have to do some calculations and come up with effective properties. So the way to do it, but we look at it, so this particular material I'm talking about, what we call a plain view carbon fiber laminate. So similar to our clothes, this view pattern is a plain view. And then if you look at carefully, this pattern is repeating. So we take a repetitive unit cell pattern, and then we try to model it in computer as a material model. And then you have to look at the micrograph, get these properties, the waves, cross-sectional area, waveforms, and all those things correct. And then you can simulate in the computer. They are using here the periodic boundary conditions and using the virtual work principle. I'll not go into technical details too much, but basically what you can do is go through these principles, and then you can come up with this effective property, which comes as an APD stiffness matrix, which is well known in composite structures. And then once you have that, you can see the properties you are getting. Are those correct? You have to always verify what you are getting. You cannot blindly believe the computer. Okay. And then once that is ready, there's a different concept. So what I took is only one unit cell. And then if you look at this wave pattern, so here I have two layers. So if you look carefully, like in wave theory, we talk about in phase and out of phase. So here these two are parallel. If you look at the fiber going in the longitudinal, so parallel to the display. Here it's both are going in parallel, out of phase, both are going in 180 phase difference. And then we took one unit cell here, but what about using different size of unit cell, whether there's a size effect? So all of those things you have to be carefully analyzed. And then of course, as I said earlier, you have to always verify your prediction. So in this particular case, we were able to fairly well match. And then we are ready to come up with this simulation. So now in my material model or the computer structural model, I'm putting these properties here, and then I'm trying to see whether we can simulate. So the way that so what you're seeing here is the exact same image I showed you. You have two arms here rotating. So that the idea here is to look at this. This is going to be fall rotated and then deployed. So what we need to find out is the bending moment and the torque. So this is the configuration we have here, and I'm modeling the same thing in the computer using the similar boundary conditions. So one of the things in this structure, probably you saw that I cannot bend it like this. If that happens, it's going to break. So I had to pinch in the middle, and then only I can fall. So practically this cannot be bent like that. I'll come back to that why it happens. So then the idea is first you pinch, and then you rotate, and then you will achieve the 180-degree fall that we do. So what you're seeing here is the computer simulation of this. What I'm plotting here is the energy variation, and what I'm plotting here is the moment versus time curve. As you can see, the localized faulting, there's contact, so highly nonlinear geometric condition, highly nonlinear material properties as well. And then it can be folded. And then I'm going to deploy and see whether it can come back to the original configuration. So while you're looking at that, please note that there are these high peaks in moments to curves. I'll come back to that. That is an important phenomena in these structures. So as you can see, it fully recovers back and no additional strain. So it's zero energy and we are able to simulate it. Now, when we can do the simulations, as you can see, the stored energy is this much, so it allows us to do the calculation and see how it behaves. And then at the end, the energy becomes zero. Now, as I told you, this particular structure you cannot physically bend because it's going to break. Whereas in the computer simulations, you can do that. And if you can look at it, the central part here, what you're seeing here is this dark color line is while you are folding, and then the gray color line or the gray color continuous line is while you are unfolding. So as you can see here, while folding, it has a very high peak. So basically, if I'm trying to pull it, bend it like this, it's locked into position because of the high peak. So you have to go beyond this peak in order to bend this. So that is called latching, and it's very extremely important because once the structure deployed to full configuration, if you have this latching force, it will not allow you to it will not be flexible. It has to be stiff. So that is very important once you deploy. Then what I look at is the static configuration. Now, as you see, this is a dynamic configuration, inertia based rod. So how we can analyze that? So what you're seeing here is, as I said, we are using a gravity offload system. And this is the particular hinge I showed you. And we have attached an aluminium tube to one thing to simulate another structural component, as well as this additional energy will slow this down. So what you're seeing here is the same configuration. This same hinge is bent into 90 degrees. I have a high-speed camera directly looking at this particular hinge. And then what I'm showing you right now is the real-time video with a normal camera. As you can see, this does not latch, it goes out and come back, which is not what we really want. And then if you think about the structure, at the beginning, it's a symmetric structure, whereas you can see, so let me explain first, this black color object you are seeing is the actual experiment recorded through a high-speed camera. And then the green color object is the computer simulation. And I'll try to play both together. So if you carefully look after it's we want it to stop at the straight line, but it goes the other way around. And if you look at the top one, it's folded at somewhere here. The bottom one is folded somewhere here. This is not what we need, but the positive thing is computer is able to capture it. And clearly, and once it latches, you can see a torsional motion, which is not desirable in space. So we are able to capture that, which is a good thing, but then can we really do the optimization? So before that, we have to know whether the structure is failing. So we have to have a failure criterion. So there are existing failure criterion, complex criterion for fiber composites, but it does not really work in this particular case because it's a ultra thin composites. And what I'm going to present you here is we did several experiments, one of the tensile test, compression test, shear test, bending test likewise. And then with that, I'm not going to go into details, and it's probably the only equation I'm going to have in this presentation. But basically, this failure criterion has three conditions. If this value becomes larger or value becomes more than 1, that means the structure is failing. So once you have that, here I have these three equations where I call them FY1, this failure index 1, 2, and 3. This is basically axial dominated. This is bending dominated. This is coupling axial and bending coupling. So the simulation predicted that it's going to crack at this location, and we did an actual test, and it's actually cracked at the same location. So now we are confident about our simulations as well as failure criteria, and then that allows us to go into design improvements. So going along the same hinge, if you remember what I presented at the beginning, this particular structure, they did only experimental studies, trial and error process, and they came up with this particular hinge configuration. They didn't do any simulations on this level, no high fidelity simulation. So we use this as a basic structural arrangement. We parameterize in using slot width, slot length, and the end circle diameter, and then we try to play around it varying these parameters. Now, if you remember this masses booms, as I said, first they flatten this, then rotate and fold it. So if I show you the simulation, you can see first we are flattening into half the diameter of the tube. And then you can fold it and achieve what you want. So then we have the failure criteria and see whether it's failing or not. So when you do this, as I said, first we tried it and it said it's failing, and we modeled, built that as well, and we found out it's failing. And then we came up with a selector slot length of these parameters, and it worked, and we actually built it and found out it can be folded as well. Now then, once you have that, let me try to explain the final step where we can actually use this in an actual structural configuration. So the idea here is you have a 1 meter long boom wrapped around the spacecraft, rigidly connected to it. And one condition is once this deploy, it has to fully latch. It should not go beyond this point. If you remember the previous hinge, it actually went in, which is undesirable, what we call overshooting. There should not be any overshoot. So now this is an example of overshooting. So I have this spacecraft here wrapped around. It starts deploying from this point. You can see clearly initially only this hinge rotates, not the other one. So it's important to know how it behaves. And then after that, but we have to stop it here, but it actually went out. So then we did further improvement to the design. And finally, we came up with a design where it's fully latched. So now the next step is computer said this can actually be true or whether it will work. So we did an experiment. I'm not going to go into details too much, but what you're seeing here is the real-time video, and this will be the high-speed video as I shown you earlier with the different hinge. So as you can see, this rapidly deploys and it does not overshoot. And this is the slow motion video taken through a high-speed camera. So hopefully, I hope that you got an idea about the overall design process of a deployable boom. So now this actually is a project later on happened with the Caltech, University of Surrey, and Jet Propulsion Laboratory, NASA Jet Propulsion Laboratory. Here the mission is that they have 4 what we call CubeSats, small satellites. These 4 can separate and fly with respect to each other. So the idea is that there are some mirrors where we focus on the certain, let's say a star or something. So depending on the configuration, you can change the focal length. So if you look at the middle part of it, these are arranged in a box type of structure, whereas this is more in a linear. So you need a camera further away from this so that you can observe the position of these, and then they can talk to each other and reposition. So in order to get this camera, it has to attach to something. So the idea, they came up with a similar hinge, a similar boom with which had 4 slots, and then they can. So it's actually being used right now. And then I'll show you one final example which relates to this. This is Caltech Space Solar Power Project, state of the art. I'll go through details. But the idea here is basically you're talking about the space solar power. If you are on Earth, you get cloud cover, rain, and day and night. All those things are going to affect you. Whereas if you have your solar sails in space, you get almost unlimited power. Of course, depending on the location, the positioning. And then if you have a system where you can wirelessly transfer that energy onto Earth, that will be definitely an advantage. One is the efficiency, other one is the location. Now, you cannot have cables. The earlier system, this concept has been there from 1940s. But the problem is they have been thinking of using X-rays, which basically evaporate anything coming through that, whether it's an aeroplane or a bird. But now they are going into radio frequencies and trying to see whether it can be done. That is one challenge. And the other thing is, I'll play the video, then it will be much more clear. You have photovoltaics, and then the backing structure is the structural component, and then also a frequency, a signal processing, where we direct this power. That's more sort of electronics. So the three professors at Caltech, one from electronics, one from materials, and my supervisor who's from structures, are developing this. So they actually sent this to space in December, and now they are trying. So the idea here is that you will have several satellites, one of these block, and then this is the moonflower that I talked to you about. The deployable concept here is the moonflower. And these are laboratory scale experiments. So this is the structural components, but then you have the photovoltaics, structural stiffness, as well as the RF layer. So there are three layers. So this is a true multidisciplinary project where you have to bring all three together, and they were able to do it in a single layer. Structural stiffness, electronics, as well as communications. And so what we call is a tile. This will be combined with several, and what the unit you saw is this one. And then there will be several of these spacecraft flying around Earth. And then if they can channel the energy to the correct place they want, it can be even middle of Africa, desert, or during war as well. So what you're seeing here is the actual experiment, laboratory scale experiment. What you see here is the tile, and this is the receiver. As you can see, when you put your hand, it's going to block. So this wireless power is already there, commercially available. But the idea here is it's put it into space, and whether you can transfer it through space at a long distance and location. So it's actually being tested right now in space as well. So with that, I'll just quickly go through a couple of other sites that I'm working on. So with regard to the same thing, now one of the problems is here you can see, if you look at these structures, it's curved highly. Whether you can break that. I mean, this particular material will break at a certain curvature. Whereas, so that's a limitation in compaction. And then also we are looking at, our model was initially linear model. Now we are trying to see whether we can capture the nonlinear part. And then this is another example where you use two different materials. This is the silicon, where it allows you to go into a very small country, almost 180-degree fault, and it will not break. And then coilable booms, what is used in space structures, so that example I showed you. There are different, I will not go into detail. So this is the exact Caltech solar power project, they are using this. And then if you think about these booms, it's an example where NASA is planning to use coilable booms in, let's say, a moon habitat or a Mars habitat. So you can come up with all these as the deployable structures. This is lightweight, as well as you have to erect rapidly. So if you make out of this steel, it can be used even on Earth. And also depending on the type of configuration and the stiffness, it can be permanent or temporary. And then I did not talk about the membrane structure. There are a lot of work going on in that area. The membrane wrinkling as well as crease locations, all those things are important. So with that, I would like to acknowledge the funding agencies, the Hinge Commonwealth Trust, California Institute of Technology, National Research Council, National Research Foundation Sri Lanka, in the Sri Lanka Joint Research Program, University of Colorado, of course, and Ceylon Steel Corporation. Any professor would say all what you present is because of you had good students. So as Prof has alluded to, I was being very lucky to have very good students, and as you can see, some of them went to Cambridge, some of them to Caltech, Berkeley. Likewise, they are all over the world. Actually, Sumudhu is here. I'm glad that he came back, so I would like to give my credit to all of them. And finally, I would hope so. Maybe most important part of the presentation for me is to acknowledge the people who helped me and why I'm here today. So let me start with, give me 1 minute to go through this. Let me start with my supervisor, PhD supervisor, Professor Sergio Pellegrino, who has been there and molded me as well as up to even today, he's been guiding me and helping me. And several, I mean, this is only a small group. I had so many, and most of them are professors in US right now, including Stanford. So I'm glad that I had experience with them. And of course, coming back to Moratuwa, Professor Dias is the reason, in fact, I'm here today, not only at Moratuwa, but in academia itself. My father is an engineer in the industry. I wanted to go to industry. So in his introduction, he mentioned about me in final year, I work with him. So that is the time I actually got thinking about higher studies. So to date, I'm actually grateful to him that I got this opportunity and molding me. And then Madam Mallikarachchi is the one actually who sort of inspired me in design, who taught me design. Thank you, Madam. And Amika Madam is the one who taught me ABC of structural engineering. And Professor Rohan Veerasekara was the first one to do analysis and certain things. And also he's one of the people who actually keep on telling me like, okay, you have to come back, not to force, but encouraging me to come back to Sri Lanka. And of course, Professor Tishan Jayasinghe has been inspiring everyone to like dream big. So unfortunately, at my time, I didn't have much interaction with Professor Nanayakkara because I think he took a sabbatical on that particular year. But of course, after coming back, he's one of the main people who guided me as a researcher, as well as the teacher, as well as academic administrator. And so, as you can see, I'm getting the structures group a lot because, of course, I'm in structures and I'm inspired to do structures. One person that I would never forget is Professor Vikram Surya. Actually, when I was in the university, I was not a talkative or like a forward person. So Professor Vikram Surya got me into this mentoring program at the department, and he's the one who actually pushed me to. So in a way that I'm in front of you today, maybe because of him. I also had a mentor from India, Mr. Shivaram Krishna Mallela, who's a mechanical engineer who helped me a lot. And there are a couple of others who are not here, but used to be in structural engineering division before. Dr. Ms. Manoja Veerasinghe is my advisor throughout the civil engineering program, and Dr. Kirti Ranasinghe is my undergraduate supervisor who in fact introduced me to Professor Dias, even though Professor Dias taught me in the second semester. And Professor Jagat Manatunga has been helping me a lot, especially with the grants and funding. And Professor Rajit Rajapaksa, I always go and talk to him at any time. And also, I don't have the photograph here, but Professor Gudatilak is the one who helped me a lot. And when I applied for the project, he's the one who's the head of the department. And Professor Ms. Jayasinghe is the one who was head when I was actually went through the interviews, and he has been helping me a lot. And two friends who sit together in grade 6 in the same bench. All three of us came to Moratuwa, and two of them in computer science. And they are the one who really dragged me into, and I'm glad to and proud to say that all three got PhDs from UK. And then when I come to Moratuwa, these are the two people, Loshika and Samir, who were continuous throughout with me today. And then most importantly, my family, my father, mother, and the two brothers. And finally, my wife and daughter who have been always pushing me and encouraging me. Thank you very much.
Thank you, Professor Chinthaka. That's captivating. Yes, I think you did real justice to an inaugural lecture, and maybe we should look forward to doing structural engineering. Right, may I invite Professor Gudatilak to hand over to the conversation power. Thank you. That brings to the end, but let me just take a minute in acknowledging our sponsors to have the inaugural lecture at University of Moratuwa. Cargill's as the event sponsor, Daily FT as the print media sponsor. We carry on the news in print media. And of course, the Sri Lankan Scientist as the social media sponsor. It's the only Sri Lankan science magazine they carry. Thank you very much, and thank you all for coming and joining for this wonderful lecture. And till we meet again, goodbye.